Section 1.3 is all about linear functions. Hopefully, linear functions are already somewhat familiar to you. I'm sure you've seen functions in the form y equals mx plus b. But now that we know more about function notation, we're going to call it f of x equals mx plus b, where m and b exist in the real numbers. A linear function exhibits a constant rate of change, which we call the slope. Notice how this is the formula we also use for average rate of change, but since we're dealing with a straight line, that rate of change is going to be constant. The graph of a linear function is a line with a y-intercept of 0, b, so whatever this number is, and a slope of m, whatever this number is. So let's look at a couple of examples. The first example is in context. It says the temperature of an oven over a 10-minute interval can be modeled by T of T equals 30T plus 75 for T in between 0 and 10, where big T is the temperature in degrees Fahrenheit and little t is the time in minutes. So our job is to complete the table and sketch a graph of the function. If I know that little t is 0, to figure out big T, all I have to do is substitute little t into my equation, 30t plus 75. So I'm going to zoom in a little bit. I know my equation is 30t, but t is now 0, plus 75. And when I do my order of operations there, 30 times 0 is 0, plus 75 is 75. I'm going to do the same thing for these other little t's. So 30 times 1 plus 75. 30 times 1 is 30, plus 75 is 105. 30 times 2 plus 75. 30 times 2 is 60, plus 75 is 135. Now if I plug in the number 9, 30 times 9 plus 75, I know that 30 times 9 is 270, and if you do need your calculator to do 270 plus 75, you get 345. And finally, when I plug in 10, 30 times 10 plus 75, 300 plus 75 is 375. Notice here on your table, every time the time goes up by 1 minute, the temperature of the oven goes up by 30 degrees, which we can also see in our equation is our slope. Additionally, when time is 0 minutes, the temperature of the oven is 75 degrees, which we see here is our y-intercept. So now that we have a table that represents this function, we can go ahead and graph our points. So I can plot the point 0, 75. Again, I look on my graph and I see the small t is here, the big T is here. So the point 0, 75 would be on the y-axis at 75. I also have the point 1, 105. So I'm going to have to do some estimating here. 2, 135. So let's see, I've got 125. 135 is going to be somewhere in here. 9, 345. So here I'm at 300, 325, 350. It's going to be somewhere over here. And 10, 375. 375 is going to be here's 300, 25, 50, 375. Okay. And then if you have a straight edge, I would highly recommend using a straight edge. It's going to be a little tricky for me to use a straight edge on my Surface Pro screen, but I'm going to try to make this line as straight as possible. And then I'm actually going to end this line with an arrow because it could go on forever. However, now that I'm looking at this, I realize that I am actually given a domain here for temperatures between, or for times between 0 and 10 minutes. So actually, I'm not going to include an arrow here. I'm just going to end it at the 10 minutes. That's a good thing to always look at in the context of the problem, is if you're given a domain or not. All right, moving on. What is the t-intercept of this function? Really, I'm asking what the y-intercept is, since on our y-axis, we're talking about big T for temperature. The y-intercept or the t-intercept of this function is 0,75. We can see that both on our table and our graph, which means at 0 minutes, the oven's temperature is 75 degrees. What is the slope of this function and what does it represent in the context of the situation? Again, we already talked about slope. We can see that in our equation up here, and we can also see that for every 1 minute that passes, the temperature of the oven increases by 30 degrees. So the slope of the function is 30, and we would say the temperature of the oven increases by 30 degrees Fahrenheit each minute. Moving on to the next example. Here is a graph of the function y equals f of x. There is no context around it. It's just a function that we're calling f of x. So I want to evaluate f of 3 and f of 5. Again, with function notation, this 3 and this 5 are both x values. So I can look at my graph and determine that when x is 3, go up to my graph and figure out that y is 2. So I would write f of 3 equals 2. Similarly, for f of 5, when x is 5, I go up to my graph, and I'm going to have to estimate a little bit here. It's not quite 1. Maybe we'll say f of 5 equals like 0.8, something like that. Find the x and y intercepts. The y-intercept I can very clearly see on my graph happens at 0,4, and the x-intercept, where my graph crosses the x-axis, happens here at 6,0. End behavior. We need to remember our limit notation. So the limit as x approaches negative infinity of f of x, and the limit as x approaches positive infinity of f of x. For the first one, as the x values get infinitely small, so as my eyes move towards the left, the function itself is going up towards positive infinity. For the limit on the right side, as my eyes move to the right and as x gets infinitely big, my eyes go down, which means that it approaches negative infinity. On what intervals is f negative or below the x-axis? Starts here and it goes forever to the right. So we would say from 6 to infinity. Lastly, we want to find the equation for f of x. So if I know this is a linear function, I know I'm dealing with an equation in the form of mx plus b. I know that my y-intercept is up here at the 4, so I'll put a plus 4. My job now is to determine my slope. So I can count in between two nice points, rise over run. Between these 2 points, I would go down 2 and to the right 3. Now, it might be helpful in this situation to go back up to part A, evaluating f of 3 and f of 5, just to make sure that we did things correctly. Another way I can evaluate f of 3 is to now plug 3 into this equation, negative 2/3 times 3 plus 4. When I do that, negative 2/3 times 3, well, I can put this 3 over 1 if I wanted to, if I didn't have a calculator. Negative 2 times the top 3 is negative 6. 3 times 1 is 3. And I know that negative 6 over 3 reduces to negative 2 plus 4 reduces to positive 2, which happens to be what I got here when I looked at my graph. Now, if I try f of 5, the one that we did have to kind of estimate, I can probably get a more exact answer. So negative 2/3 times 5 plus 4. Negative 2 times 5 is negative 10. Negative 10 divided by 3, let's see, that would be negative 3.333 plus 4. So it looks like we may have been just a little bit off on our estimation. If you need to use your calculator for those decimals, and you type in 3.333 negative plus 4, you get 0.667. So we were a little off on our estimation, so it's always good if we do have an equation to check our work with that equation.